Good morning, everyone. Today I'll be presenting my heuristic construction for solving a non-routine mathematical problem using computational thinking in 21st century learning. In this presentation, I will not only focus on obtaining the final answer, but more importantly, I will explain the thinking process behind solving the problem. In modern education, especially in the 21st century, the way we think and approve problems is just as important as the solution itself. Through this presentation, I aim to demonstrate how a real-world problem can be transformed into a mathematical model and solved systematically using computational thinking. To begin with, let us understand what a non-routine mathematical problem is. A non-routine problem is a type of problem that cannot be solved directly using memorized formulas or standard procedures. When students first encounter such a problem, they may not immediately know what steps to take. Instead, they must carefully analyze the situation, interpret the given information, and decide on an appropriate strategy. This is very different from routine problems, where the steps are already familiar. For example, solving a linear equation like 2x plus 5 equals 15 is considered a routine problem because students already know the procedure. However, in a non-routine problem, such as designing a container to maximize its volume, students must first determine how to represent the problem mathematically before they can even begin solving it. This additional layer of thinking makes non-routine problems more complex and meaningful. Non-routine problems have several important characteristics that distinguish them from routine problems. Firstly, they do not have an obvious starting point. Students often need to spend time understanding the problem before deciding how to proceed. This uncertainty encourages deeper thinking. Secondly, these problems require higher order thinking skills, also known as HOTS. This includes the ability to analyze the problem, evaluate different strategies, and sometimes even create new methods of solving it. Thirdly, non-routine problems encourage creativity and flexibility in thinking. Different students may approach the same problem in different ways, and each approach can lead to a valid solution. For instance, one student might solve a problem using algebra, while another might use graphical methods. This diversity of approaches enriches the learning experience. Finally, non-routine problems often involve trial and errors. Students may test different ideas, make mistakes, and refine their strategies. This process is valuable because it helps develop persistence and problem-solving resilience. Now, let's us compare routine and non-routine problems in more detail. Routine problems are usually straightforward and predictable. They follow a fixed structure, and students can solve them by applying known formulas or procedures. These problems are useful for practicing basic skills, but they do not require much critical thinking. On the other hand, non-routine problems are more complex and open-ended. They do not provide clear instructions on how to solve them. Instead, students must think independently and decide on the best strategy. For example, a routine problem might ask you to calculate the area of a rectangle using a formula. In contrast, a non-routine problem might ask you to design a shape with the maximum possible area under certain conditions. In this case, students must first understand the constraints and then develop a strategy to optimize the area. This comparison shows that non-routine problems play a crucial role in developing deeper understanding and independent thinking. Non-routine problems are extremely important in 21st century learning. In real-life situations, problems are rarely straightforward. We are often required to analyze complex situations, make decisions, and adapt our strategies based on changing conditions. For example, in fields such as engineering, business, and technology, professionals are constantly faced with problems that do not have clear solutions. They must think critically, evaluate different options, and choose the most effective approach. Non routine problems help students develop These essential skills, they encourage independent learning as students cannot rely solely on memorization. Instead, they must actively engage with the problem and think for themselves. In addition, these problems promote creativity and innovation, which are highly valued in today's world. By practicing non-routine problem solving, students become better prepared for real-world challenges. So now I will introduce the problem that I selected for this task. The problem involves constructing an open-top container from a rectangular sheet of material. In this process, equal squares are cut from each corner of the sheet, and the sides are folded up to form a box. The objective is to determine the size of the square cut represented by X that will produce the maximum volume of the container. This problem is particularly interesting because it combines multiple areas of mathematics, including geometry, algebra, and calculus. It also reflects a real-life situation, such as designing packaging that can hold the maximum amount of the product while using a limited amount of material. This problem is considered non-routine for several reasons. Firstly, it does not provide a direct formula or method for solving it. Students must first interpret the situation and decide how to represent it mathematically. Secondly, the problem requires the construction of a mathematical model. This means that students must translate a real-world situation into mathematical expressions, which is not always straightforward. Thirdly, there are multiple ways to approach the problem. For example, students can use differentiation to find the maximum value, or they can use graphical methods to estimate the solution. Some students might even use trial and error by testing different values of x and comparing the resulting volumes. This variety of approaches highlights the flexibility required in solving non-routine problems. To solve this problem, we first need to represent it mathematically. Let us assume that the original length of the sheets is L and the width is W. Let X represent the size of the square that is cut from each corner. After cutting and folding the sheet, the dimensions of the box change. The new length becomes L minus 2x because we remove x from both sides. Similarly, the new width becomes W minus 2x and the height of the box becomes x. Using these dimensions, we can form the volume function as V of x equals x multiplied by L minus 2x multiplied by W minus 2x. This step is crucial because it transforms the real-world problem into mathematical model that we can analyze and solve. Now I will introduce the concept of computational thinking. Computational thinking is a problem-solving approach that involves breaking down complex problems into smaller parts and solving them systematically. It is widely used in computer science, but it is also very useful in mathematics and other disciplines. Computational thinking consists of five main components: decomposition, pattern recognition, abstraction, algorithm design, and logical reasoning. By applying these components, we can approach complex problems in a structured and organized way. The first component is decomposition. Decomposition involves breaking down a complex problem into smaller, more manageable parts. Instead of trying to solve the entire problem at once, we focus on one part at a time. In this problem, we decompose it by identifying the variables, understanding how the shape changes after cutting, and determining the formula for volume. This step is important because it reduces complexity and helps us focus on solving each part systematically. The next component is pattern recognition. Pattern recognition involves identifying similarities between the current problem and problems we have encountered before. In this case, we recognize that the problem is similar to optimization problems in calculus, where we aim to find the maximum or minimum values of a function. By recognizing this pattern, we know that differentiation can be used to find the critical points of the function, which helps us determine the maximum value. The third component is abstraction. Abstraction involves focusing only on the relevant information and ignoring unnecessary details. In this problem, we only consider the dimensions of the box and the variable x. We ignore factors such as the material or color of the sheets as they do not affect the calculation. This simplification allows us to represent the problem as a mathematical function, making it easier to analyze. The fourth component is algorithm design. Algorithm design involves creating a clear sequence of steps to solve the problem. In this case, the steps include defining the variables, constructing the volume function, differentiating the function, solving for the critical points, and also verifying the maximum value. Having a structured procedure ensures that we do not miss any important steps and helps us solve the problem more efficiently. The final component is logical reasoning and evaluation. After obtaining a solution, we must check whether it is valid and meaningful. For example, the value of x must be positive and must not exceed half of the length or width. Otherwise, the box cannot form. We also need to verify that the solution gives a maximum value, not a minimum. This can be done using methods such as the second derivative test or graph analysis. This step ensures that our solution is both mathematically correct and practically applicable. Theories such as GeoGebra plays an important role in this process. By plotting the graph of the volume function, we can visually identify the maximum point. This helps us confirm our calculations and improves our understanding of the function. In addition, using technology makes the learning process more interactive and engaging. Computational thinking and non-routine problem solving are closely related. Computational thinking provides a structured framework that helps us approach complex problems step by step. Without computational thinking, non-routine problems may seem confusing and difficult. However, by applying decomposition, pattern recognition, abstraction, and other components, we can simplify the problem and solve it more effectively. Heuristics are strategies or guidelines that help us solve problems. They do not guarantee a solution, but they provide a direction and help us make decisions. In this problem, the heuristic approach guides us from understanding the problem to forming a mathematical model and finally to solving it. This structured approach improves efficiency and reduces confusion. From this task, we gain several important insights. We develop stronger problem solving skills and learn how to approach unfamiliar problems with confidence. We also improve our computational thinking skills, which are useful in many areas beyond mathematics. Most importantly, we understand how mathematics can be applied to real life situations, making learning more meaningful. However, there are some limitations to this approach. Non-routine problems can be time-consuming and may be challenging for students who are not used to independent thinking. They also require a strong understanding of concepts, and the multiple steps involved may increase the risk of errors. Despite these challenges, they are still valuable for developing important skills. In conclusion, non-routine mathematical problems are essential for developing higher order thinking skills. By applying computational thinking, we can solve these problems in a structured and systematic way. Heuristics provide guidance throughout the process and help us reach meaningful solutions. Overall, the approach not only improves our mathematical abilities but also prepares us for real world problem solving. That's all from me. Thank you for your attention.